All right, and so now that after we have seen example 1 in our topics about in our topic discussion about definite integral, then let's look into some further and some actual properties of a definite integral over here. Okay, so now with the properties, so here I'm calling that properties. Okay, of a definite integral. Okay, so now with some of these properties, I have to mention ahead of time before we start getting into it. Some properties come out quite straightforward, okay, and some other properties I do need to bring up a little bit of math work right there to make it clear, okay. But in the end, they should all be decent enough for us to understand and be able to use. And these are the practical, very practical properties that we can use them. Okay, so again, nail down in your mind now that a definite integral is accumulation. And so far throughout the work, I've been doing that visual demonstration that I've been accumulating all the stripes with thickness dx with the height at f of x, right? And accumulating all the stripes from the starting end to an ending end, right? There's a start and there's an end of where your accumulation goes. So the first property I see that now is, now you have a function and you're accumulating all the stripes with the height f of x and thickness dx, okay, and multiplying that to get you the area, kind of like that's how we visualizing. But now we're accumulating from A to A. It looks a little surprised, isn't it? It looks a little shocking, isn't it? But it's a one truth now that comes out as the way how we define a definite integral as accumulation. So think about a function. Think about your function. You're at A, and you got a stripe right there with thickness dx, and you're not accumulating anywhere other than just A. You're accumulating right at that stripe only. And so needless to say, if you stay right there, see, the integral he's saying we're accumulating is saying that we're accumulating from A to A. Okay, so needless to say, now if it's only at that only one stripe, then we can say that we're at 0. We're not, the only thing we have is 0 area. That's it. Okay, that's it. And so in that way, now from now on, anytime you're looking at accumulation, okay, a definite integral, but unfortunately, or someone might see that as not as unfortunate, okay, but we're accumulating on the other hand from A to A itself, we're standing at the same spot. Then that definite integral has to be just simply a 0, okay, and so that would be one of the special property that we got to nail it down first, okay. And so now, aside from that, these are quite a few common properties right here that I would like to start bringing it up right here. All right, and so we can call this property number 1. And then many textbooks can put these properties in different orders, and I have my own order as well. It depends on how I feel that's good for the learning of the students of mine, or the learning of the viewers who are watching this video. So this is how I see the first property, okay. And so now here's another property that I want to point out over here. Okay, property number 2. So you have seen that earlier in our example 1 at the end of example where I had when we try to handle a definite integral as in terms of by interpreting that as an area, and we saw that in the end we had to break it up. We had to break it up into into two separate areas, and then in the end it's accumulation. Again, I constantly remind anyone it's accumulation. So in the end, even though we broke it down into two separate accumulation, but in the end it was 2 separate areas that we were accumulating together, if we were thinking of that in terms of a picture. So that actually implies another important fact that, see, think about this picture over here. In that problem, if you think that as the starting is an A and the ending of the accumulation is at B, and we had a C point in between, then we can, this total integral from A to B on the function there, okay, that total one can be broken up as, so now let me demonstrate. This one on the right hand side here from C to B is a separate accumulation from C to B, okay, of the function f of x, same function f of x dx, and this other separate one. So I'm making this generalization right out from part C of our example 1 we just done prior to this point right here. And so this left triangle here came out as a consequence of accumulating stripes from A to C. And again, in how I explained earlier, C is a value somewhere inside of the total interval from A to B. And so now think about it. You can either think of that in terms of area or as accumulation, but in the end, this total accumulation, I just said the total accumulation has to be a accumulation of these two separate accumulation works. Okay? And so in that way, now I'm breaking it down as see, the integral, the definite integral accumulating from A to C added up with the definite integral accumulating from C to B on that function. Okay, so we achieved that relationship right here. So after that explanation, and so now we can formalize, we can formally put that into a property as followed, and allow me to go a little bit wordy here, but okay, let C be a value that stays anywhere inside the interval from A to B. Okay, anywhere, so C is a value anywhere inside of the interval from A to B. And as a picture again, see, A is here, B is here, C is somewhere inside. So two accumulation work come up with for us, added up together, give us the total accumulation work from A to B. Okay, so in that way, once we had that satisfied, then the total accumulation from A to B on our function f of x, it will definitely equal to the accumulation work, the integral that's accumulating from A to C on this same function. Okay, and we're adding that with a separate integral accumulating all the stripes from C to B on the same function. All right, and that is another important property that comes straight out in the way how we're thinking of definite integral as accumulation. Okay, and so it's another one that we can utilize that and apply that in a lot of places and when we handle and solve a definite integral problem. And that I call that here property number 2, because I feel it's so straightforward. It comes right out as a consequence of understanding a definite integral as accumulation. Okay, and so now I'm going to step over to my other board, and I'm going to introduce a few other properties there. All right, so with these properties here, then some of those are easy to illustrate, but some of those these I'm about to introduce are also a little more challenging. So I have to bring in a little bit of math like that to explain. Okay, so be patient with me here on these. So property number 3, this third property here. So anytime we are doing a definite integral that's accumulating from A to B of a function where it's simply a constant function. Okay, it's accumulation. It's an integral, a definite integral accumulating from A to B, but our function here, regardless of whichever x value that is a constant function. So C times dx. C times dx. Okay, and so now at this point, with what we have done throughout example 1 and through many times I've been explaining, then it's accumulation. So to explain this property, here's how I see this. Think of a constant function as a horizontal line, and that's the way it is. We can always visualize a constant function as a horizontal line. Okay, and for now, let's assume the easy case is a positive one. So A is here, B is here. we're accumulating from A to B, so these are the stripes. No matter where we put our x value, the stripe remains the same height, C. So it's C here, C here, C here, C here. They're all C heights right here until we reach to that ending of our accumulation. Okay, so what do you think? So at this point, naturally enough, the final, as a consequence here, the final answer to this, the final accumulation is going to come up for us. The total interval's length, B minus A, the total interval's length of the accumulation, but multiply with the height, C right there. And that gets us, or in other words, we can see that as the area of this sideways rectangle. Okay? So that's property number 3. And now, allow me to introduce the next one, property number 4. And these are the ones that are kind of all related to each other right here. So, property number 4. Now, when we're accumulating a function, okay, and our function is 2 terms, is having 2 terms. Our function is having 2 terms, so some f of x plus some g of x. Okay, having 2 terms. So many textbooks refer to this as the sum rule over here for taking a definite integral. Okay, so, but in other words, our function has 2 terms. So I'm going to get straightforward into this one right here. Anytime that we're doing an integral work, a definite integral accumulating from A to B, but our function has 2 terms, and we can always separate it out. One integral, the exact accumulation from A to B, but on f of x. And there's another separate integral from A to B again, but on the other term. Or in other words, we can take definite integral term by term in case our function is broken up into multiple terms like this. Okay? Into multiple terms like that. And so this property, I have to mention it. It does have something to do to be separated, but it's quite unlike, and that's why I want to leave that the property number 2 on the board until now. See here, there's also a separation, but the separation happened because we got a C point between that. But our function could have been just one function. Okay, it's 2 different things. But then, whereas on my sums rule just now, when we did that separation, it's just the integral bounds right here, the integral limits, the accumulation limit stays the same from A to B, from A to B. But here it's just 2 separate integral works right there. Okay, that can be added together. Okay, and so explaining this can be a little bit of a challenge right here. So just think about this. At this point, allow me to bring in the challenging definition, the ultimate definition with the limits and the Riemann sum, so to explain. Okay, because I am not very convinced with the graphical explanation of this. It's hard to see. So anyway, back to our ultimate definition, any integral. Here is f of x plus g of x, but our big function, our main function is the f of x plus g of x. That's our main function, and we're finding the integral. We're taking the definite integral from accumulating from A to B, and each stripe is having a thickness dx. And so this is our height, okay? This is our height, and this is our thickness. That's just a reminder right there, okay? But then after those, a reminder, and it's a product between the height and the thickness. But now aside from that, all of that minor reminder right here, the ultimate understanding about any definite integral is that it's a Riemann sum where we're allowing, so from A to B, first of all, from A to B, then think about each delta x here, we're breaking the total interval from A to B into n subintervals, okay? And so recall from the Riemann sum that we have to do a summing up. We're summing up all rectangles from first rectangle to n rectangles. And each of our rectangle now has a height being f of a chosen point I plus g of a chosen point ci right there. Okay? So this is sort of like a variation of our original Riemann sum definition with the limits. Okay, and then we multiply that with the dx, and that's the dx. And just now I reminded again that the dx here is always and permanently the number, the interval's length. That's why it's b minus a, and we divide that into the number of subintervals we desire. But then after that, after setting up the Riemann sum, so this is the general Riemann sum, and after that we're setting it up into a limit work. We're allowing n, we keep letting n increase and increase. Okay, we're letting n increase and increase. So in that way, so now seeing straight into this thing here, and in the end it's a sum. It's a sum. And I had a little bit of talk. I had another video lesson earlier in this about showing calculus students how to be a little more fluent with operating on a summation notation like this. And so with that, after studying from that video lesson about to become a little more fluent with operating on a summation, then you see the delta x right here as a common factor can be distributed into two separate terms. That's the first thing to understand. So that means I'm going to produce a limit letting n to infinity, but I have the sum as following: f of ci times delta x, okay, and then plus g of ci times delta x. I just simply distributed that, and then of course we're summing from 1 to n, but keep letting n increase and increase. And so now all of a sudden I realize I have a summation of two separate terms in each of my summation term right there. Then I can break it down. See, that's why. And so at this point, I highly recommend, if you're not feeling comfortable with any of the summation step right here, I have that video that I gave in the lecture as a lecturer before I created this, before I recorded this video, so that I talked about how we can work a little more, and especially the problem there was a little more intense to get you fluent with operating on the summation notation. So here, since we realize that this notation contains two separate subterms in each of our summation terms, so now we can produce that legally as one separate sum of ci, f of ci times delta x. That's one of it, taking the limits, okay, I from 1 to n, and then we're adding that to another one. Okay, there's another sum right here, or the g function on ci times the delta x. Okay, and then we take the limits here, two separate independent problems right there. Okay, and then once we're done, we're adding these two together. But so now what do we realize? Have a moment to realize about these. That is exactly, so this first piece right here where I put a square bracket underneath, that is exactly now on my other board. So again, what I saw here, this Riemann sum with the limits, where we had that brackets underlined right there, now can be understood without understanding of a definite integral. That is the definite integral from a to b. Okay, but it's f of x dx. Okay, that's what the Riemann sum with the limits turned out to be. And then we're going to add, and then for the other one, now I'm going to do another separate brackets underneath that part right there. Okay, so with this bracket right here, as n gets to as n increase to infinity, then that produced for us consequently as a definite integral accumulating from a to b again, but on specifically the function g of x dx. And so that's how all together in the end I have just now, and it's not a formal proof, but it points out enough detail to convince anyone that, so now when you're looking at accumulation work, and in your case where the function that you're accumulating has multiple terms, then you can just simply break it up into term by term and doing your accumulation work term by term. And so you only see this once in a while that I have to do this, but throughout the rest of your learning time with me for integral calculus, I don't always have to do this, because in the end, even though an integral calculus, but we're still a beginner into the calculus work and all of the mathematical analysis thing. Okay, so there will be more detailed proof in your standard calculus textbook, or even more detailed proof of this property that can be offered in a course in mathematical analysis. Okay, and so now That is the fourth property. And so, many textbooks try to write the next one here as a separate one, but I see that as a 2. I see the 2 as one formula. And so, now allow me to do as following. I'm going to grab a red marker. And so, the same, I still see this as the same property with number 4 right here. But in case your overall function has multiple terms but connected by a subtraction, 2 terms or multiple terms but subtraction between the terms here, then it's very similar. We have to, instead of adding here, it's going to be a subtraction. Okay? And anytime it comes to subtraction, we just need to be careful with the order. So in the beginning, before we separate it out, then f of x came before the minus sign, before the subtraction sign, and g of x came after the subtraction sign. And so here the order of the 2 definite integral works have to come exactly as how it started in the beginning. So the integral on the f function subtract the integral, the accumulation on the g function. Okay? So generally speaking, the entire property number 4 is all about anytime that your function is multiple term, either adding or subtracting between the 2 terms, then we can do 2 separate integrals and either add or subtract the 2 integrals. Okay, the 2 definite integrals. And that's how I can combine 2 properties into one like that. So here you can also refer to this as a sum or difference. Okay, the sum or difference rule or property when you're taking the definite integral, any definite integral. Okay? And now let's step over to my other board. And look at the 5th property. And so now with the 5th property, this is what I'm seeing. We're having an integral accumulating from a to b, a definite integral accumulating from a to b. And our function here comes with a coefficient c, a constant coefficient. Okay. Then this can be found as, the answer here can be found as, we can just simply produce the answer, the definite integral from a to b only on the function f of x, and then multiply the constant in front, the constant coefficient in front. Okay, and so that's a property, and I can just quickly illustrate. It's not a formal proof, but I can illustrate the idea as following. Think about that constant coefficient as a 2, for example, 2 or 3. So if you're looking at 3 times f of x dx, for example, this is just one way of how we explain this, and there are tons of other ways. And formally speaking, to get a formal proof, you can search into any standard calculus textbooks to get, but as a quick demonstration to convince anyone, because I don't want to waste any one of your time, when it's not necessary to go through all of these proofs here. But 3 times f of x means inside of this integral, we can think of that we have 3 terms, f of x plus f of x. And I'm just making up some arbitrary constant coefficient like that. So for now, if it's a 3, then think about it's f of x plus f of x plus f of x. So it's, in the end, it's a function with 3 separate terms, f of x, f of x, f of x, and dx. And so with the sum and difference rule we just learned previously, prior to this one right here, then we can separate down into, okay, one of them is for f of x plus another integral accumulating from a to b on f of x, and the third one here, okay, with the dx. And so with 3 of them being identically the same right there, then we have our reason to call this. This is 3 times of that, 3 times of one integral accumulating from a to b, but we triple it. That's how it is. Okay, and so now from now on, anytime you're in your definite integral work and you found a function being multiplied by a constant coefficient, you can easily find accumulation on that function itself individually, and we put the constant coefficient, we multiply that with the constant coefficient at the end. Okay, that's what this rule, this property allows you to. Okay. All right, and so now here we are at property number 6 right here. All right, so property number 6. And so I have to start out saying that if we have one function f of x known to be lower than or at most equal another function, so f of x is less than or equal to g of x. Or you can also say that if we have some function g of x being greater than or at least f of x, then here's one thing we can always see here. Then and how about to be precise, let f of x, at least we recognize this property, this the inequality between the two functions over an interval, over a finite interval from a to b. I should have had that right from the beginning. Okay. Then once we know that nature between the two functions, specifically in an interval, then the integral, the definite integral of the function f of x from a to b will definitely be, okay, so be less than or equal to that definite integral accumulating from a to b on the function g of x with the dx. Okay, so anytime we have that property, then and over an interval, then consequently it will come to this result right here. Okay, and so I can also illustrate this through a graph. So we imagine we can, so at this point be flexible. Sometimes I have to use, sometimes we can use this Riemann sum to make clear a certain property, or as a truth about property, about definite integral. Or sometimes I can just use a picture as a visualization of an integral to explain why it has that property. Okay, so in this case, f of x at least over the interval from a to b. In an interval from a to b, at least if we know that f of x is below some g of x. So the curve I draw above, at least in this interval I recognize, that f of x is down here. This curve below is f of x, and this curve above is the g of x. And if that's so, now when we're accumulating. And so the area, now you can see that the area, as we visualize it, the area for g of x will be for sure larger the area for f of x, because the area for f of x is under here. Okay, and that's why we have this property right here being satisfied. Okay, and it's again, it's some point for our class here at the beginning level of calculus, we're not required to see formal proof, but here I just bring the illustration to point out how it works and how it was true right there. And then as anyone has that desire to see a formal proof, you got to search into a formal or a standard calculus textbook, and it has a proof there all over. Okay, or even a textbook for mathematical analysis. Okay, so that's property number 6 right there. So right from that property, that will produce another consequence for us. So we come into property number 7. That states the following. So usually I see property 7 I'm about to introduce here is a consequence. Property number 6 that I've seen. Okay? And so, and at this point I have to admit, the order of how I place these properties comes out as how I feel the learning for student is, but it's completely different with any textbooks right there. So don't just read my order here. Once you watch my video, you can compare, and you will see any of these properties I'm showing here is from a textbook. It's from any textbook, but the order how I arrange these properties are not, or maybe won't be exactly the same as any order that the textbook is putting it. Okay. So now, as a consequence of property number 6 I've seen earlier, then here's how I see it. Anytime we recognize that our function is above a constant value m and less than or equal to another constant value big M, so there's lowercase m and capital M. These are meant to be two different constants, but f of x is trapped between That's the idea right there. F of x is trapped between, and so anytime we recognize our function is being trapped between lower m and high m right here in an interval, okay, over an interval from a to b, okay, then we will know the following property. Then the integral, the definite integral of the function f of x dx, that one will be greater than, will be estimated. So this property in particular here is useful for an estimation, and I will get to that when we get further into the estimation methods right here. But for now, I know for sure that the integral has to be greater than or equals to m times b minus a. Okay, the integral we're looking at right here, even though we still never knew the exact function what that is, but as long as we know the function is trapped between these two values, there's a lower value, there's a higher value above, and f of x is trapped between, then the integral produced over that interval will be for sure greater than or equal to m times the total interval distance b minus a. And then for sure this integral will be less than or equal capital M times b minus a right there. And so, and just back to what I was saying earlier, usually this inequality is good for us to know some estimation of our integral. So sometimes we are in the worst case where the work for finding the accumulation doesn't come immediately. Then at least with this understanding, then we will know, we will have an estimate. So this can be good as an estimate. Okay, it's an estimate for the integral. And this is not the only way to estimate, but at least this is the most natural one. Okay, and so how can I say it comes out as a, this comes out as a consequence of the property number 6 that I pointed out earlier. So now let me get on my other board. All right, so think about, we have, you see, apparently from property number 6, we know that if this satisfies, I only break it down into one side right here. If f of x is less than or equal to m, so we can recognize this as some function g right here that's being a constant function, okay, over the interval from a to b. Then we already knew that the integral of f of x, okay, will be less than or equal to the integral of g of x, which is mainly the constant m times dx from a to b. Okay, but then, hey, wait a minute, isn't this from one of the earlier properties? I already forgot the number, the property number, but from one of the earlier property we've learned that anytime we're integrating or we're accumulating values from, we're accumulating from a to b on a constant function, then it's just simply the constant itself times b minus a. And so that's why we let down to f of x dx being less than or equal to, okay, and it's accumulation, okay, and being less than or equal to b minus a. And I can do the similar work. I can do the similar work on the other ones, on the other statements. Okay. If we recognize that the function f of x is greater than or equals lowercase m in our interval a and b, okay, then the similar work will lead us down. So you have seen the work now, so allow me to start skipping the step, but that will easily lead us down to seeing that, you see, the integral from a to b of m times dx will be less than or equal to the integral, and that's right out from property number 6 again. Okay, and we accumulating from a to b on the function f of x. And that's why this one here comes out to be m times b minus a, okay, less than our integral dx. All right, and so in that way, putting it all together as one statement, that's how I can have this property number 7 as one complete statement. Anytime we're recognizing our function being trapped between two constant values like that, then two constant values, then we come up with an estimate for our overall f of x, our overall definite integral on f of x over the interval from a to b. And so that's the estimate right there. Okay, and we can also explain this graphically. There are once we understand about this accumulation, there are a lot of ways to explain to explain about some of these properties right here. It could be m is here, lowercase m is here, two separate functions, but our function f of x is trapped in between. Okay, so now in between an interval from a to b. Okay, so a hits all the way up to m as well. See, so the integral for f of x, this is f of x. Okay, so the integral for f of x is here. That's the integral. Okay, the integral, and then b minus a times m is this area. That's what it is. Okay, and then b minus a times capital M is this area. That's how we can imagine it. So the area of the function between the function and the curve inside the interval from a to b is, of course, between the double shade and that big area. Okay, all right, so that's property number 7. And so now the last property I would like to bring up. All right, and so again, after I write down this next property, which is also according to our list, it's the 8th property, right? But allow me to have my own interpretation of that, my own way to explain that. It's not necessarily the same as like the way how many other textbooks is explaining it. It's not like I'm trying to give anything unique, but it's just everyone is approaching things a little bit different, and I feel this is good for the way how my students are learning, and it's consistent with how I have been teaching about the indefinite integral. Okay, and so now here's the thing. Property number 8 is a straightforward formula, but a little bit more challenging to explain. Let's say we have a definite integral accumulating function stripes from a to b on a function f of x and with thickness dx. Okay, with all that. But now think about, so a to b, so a is the start, b is the end. But now think about this start and end. These are the start and the end of the accumulation. So think about, what if we reverse same function, thickness time, function times thickness, but reverse the accumulation from b to a. So actually, when I say use the word accumulation, it makes people think it doesn't matter which way we're accumulating, but now what's really happened here? It's actually the opposite, the negative sign of the accumulation from, so here I'm accumulating from a to b. But if I'm turning the accumulation direction around from b to a right here, then the answer will be, the opposite of the other one. Okay? So how is that possible? How is that possible? So now I have to explain by bringing up the Riemann sum here. Okay. Another consequence, you can think of this also as, in case that we're looking at an integral from b to a, right? And then we want to turn that around. We want to reverse the accumulation direction. Then we're gonna turn that into from a to b, the function f of x. Okay, but with a minus sign. So these are the two, just the interchangeable forms of that. But in the end, how does that happen? Okay, how did that happen? So I'm going to get to my other board and explain a little bit. Okay, so now back to the very important definition of a definite integral. Definite integral here, then let's say from a to b. Doesn't matter if a is on the left or b on the right. But if we're accumulating from a to b right here, in one direction, then I have been writing down and nailed this down, but there's one piece of information I didn't bother earlier to write it down, even though I mentioned many times, and now it's time to really look a little further into that. So it's a Riemann sum, okay, where at anywhere, basically, again, we break our interval. This is the important part. If it's from a to b, then each delta x is b minus a, the upper ending minus the beginning ending over n, the number of subintervals. And then from there, each subinterval, I'm going to choose a chosen point and then multiply with delta x. But again, ultimately, what I did not put it in part of my definition earlier in the video lecture was this, because at that point, I just aim at letting viewers, letting students of mine to get to know what exactly a definite integral is. And I want to emphasize on the fact that a definite integral is accumulation. Okay? But so I did not bother too much to put this to be part of our definition. But now it's important that this delta x definition is also part of our definition. So if it's from A to B, then delta x is defined as B minus A, the end of the accumulation, always the end of the accumulation minus A, minus the beginning of the accumulation divided by the number of subintervals. And that's how I produce, and so consequently when it drives into this, whatever it turns out to be, we're accumulating, we're summing from 1 to the nth rectangles, and then we take the limits, allowing the number of rectangles or subintervals increase to infinity. That's the way. Okay? So now, in the worst case, think about this. If we have accumulation that happens from B to A, so if we see the accumulation happens where it starts at B but it ends at A, B and A could still be at the same values, but now if it starts at A and start at B and end at A, whereas here it starts at A and end at B, it's the reverse of the accumulation here. Here I have f of x. Okay, then yes, it's just like that. The formula for the Riemann sums looks almost the same. We need, in each interval, we pick a chosen point, ci, in each interval, and substitute that into the function. See, nothing different with the earlier, the Riemann sum formula yet. And we're still going to multiply each height here with the width, delta x. One more thing that looks just about the same. So, just seeing the Riemann sum doesn't explain why there is a negative sign. But now think about this. Behind the scene here, the delta x here is not the same as that delta x, even though it looks the same through the formula. But the delta x here is indeed, this delta x here in this formula is actually A minus B, because one rule of thumb we keep is A minus, we always go with the ending of the accumulation minus the beginning of the accumulation, divided by the number of subintervals. Okay, so in that way, this delta x here, so now allow me to modify things a little bit. How about I call this, this is the delta x in the usual way, this is the delta x prime right here, okay, or delta prime of x. It's just the delta x in the delta x in the opposite direction, okay. So really the delta prime of x is that. But hey, what is the relationship between the delta prime of x? It's nothing derivative, okay. It's just a prime here to indicate it's a backward symbol. I mean, it's just the reverse direction. So the delta prime of x is indeed the negative of the delta x in the ordinary definition. And so in that case right there, you see, in that case, this is how I see it. Okay. In that case, when we take this, right, and put that into our formulas, then this is going to be the summation for f of c sub I times the negative delta x, okay, and summing it from 1 to n with the limits n go to infinity. But now notice there's that minus sign right there, okay, and so all of that, so negative 1 times delta x comes in front and making it a negative. Let me now move on to my other board right there. So from this result with patches now, it's the same as negative limits of the summation f of ci times delta x. Okay, so now it's not the delta prime, it's a delta x, summing from 1 to n, okay, to letting n approach infinity. So all that here we recognize it is the integral from a to b of f of x dx. And so, but now with that minus sign here, it becomes a minus. Okay, so what I have just proven is just that this integral, actually this integral from b to a, starting at b, ending at a. That's how I started proving. So I gave So that's what it is. The integral from f of x, accumulating from b to a, that function. Okay, and now I just made that connection and proven that it's equals to the negative sign of the beginning integral, where the accumulation took place from a to b. The direction got opposite. Okay, and so that's the idea right there. Okay. And so just like that, in that way, just now I've proven that other result. I just now erased it. So we can multiply both sides by the negative sign, and that's how we arrive at this particular work right there. All right. And so from b to a, f of x, that's how I was starting out with the proof. Okay, and I showed that it was equal to negative of the usual one from a to b. Okay, and then in that case right here, if we multiply both sides by a negative sign, then it leads to the integral from a to b from f of x dx. Okay, can equal to the negative of b to a f of x dx. And that's just how it's making it clear with this property number 8 right there. Okay. All right, and so now let's look at a couple more examples here. And let me now call that example 2. Right. And now in my example 2 here, we start out with a couple of given integrals here. So how about we are given 2 definite integrals. So one of them is the integral from -4 to 4 of the function h of v, okay, times dv. Okay. And then this is given information, so we are given that this integral equals 6, okay, and in addition to that, we are given another integral value over here from -1 to 4. Okay, and of the same function h of v dv, and this was given to be 8.7. All right, it's 8.7. Okay, so now in that way, we want to calculate or evaluate. So after the given information that ends here, we want to evaluate. Okay, so evaluate the integral from -4 to -1 of the function h of v dv. Okay, and so now this is our goal right here. So with this function, with this example over here, it's a direct application of one of those properties that we have learned right there. So first of all, recall, and I'm going to write that on my other board right there. So recall that when we have an our function here, it can be f of x, and we can use whatever variables names in our function. That shouldn't be a part to worry about. And so now if we have accumulation that's going from a to b, or in other words, it's the definite integral. So if our definite integral going from a to b, accumulating values from a to b, and further we learn that if there's a c value, c is a value that is inside of the interval from a to b, somewhere inside of that interval, then we already knew this result right here. The integral from a to b, the accumulation from a to b, okay, can be broken up into 2 separate accumulations. One of them is from a to c, because now imagine that, okay, a to b is an interval, so c is somewhere in between a and b like that. And so if our function is like that, then the accumulation can happen as 2 separate accumulation. One is from a to c, and the other one is an accumulation from c to b. Okay, so now enough of the reminder. So that property we've learned, among the properties, this is a reminder. So on the same function, okay, we have that integral here in the beginning can be broken up into the integral from the definite integral from a to c, and we're going to add that, we're going to accumulate that. So anytime now that we're adding, think of that as a accumulation. Okay, and even the integral work itself is a accumulation. We keep adding up more area of stripes. Okay, and then there are the integral from C to B. Okay, of the same function in respect to the variable. Okay, so now if we're trying to apply this formula, this property that we've learned, and at this point I don't even have to worry about what formula number that is, what property number that is anymore. What matters is what we understand about the integral as a property of the integral. And so here as the observation, and we haven't started into the problem yet, but as the observation, it looks like, so here there's an integral from the definite integral going all the way from -4 to 4. And then this integral here, so these two given integrals, we have -1 to 4. So what I notice here, just a notice, okay, what we noticed here is that the interval given is from -4 to 4. And it's just my style that and I'm the instructor that explains here, so allow me to write all of these down. But for when you're actually doing the work here, this part when you notice, it's just to trigger up your observation, but you don't have to write this down on your paper. I mean, it's good that you write it down, but it's not required. So what I see here is from that interval, from -4 to 4, in that interval, we notice that this -1 is somewhere inside of that interval. It's just something we notice. So in my notation, -1 is a value that is inside of that interval from -4 to 4. So in that way, and if we're looking a little further into that, now other than the variable's name being a little unusual, I mean, we're more comfortable with x being the variable's name, with y being the variable's name, or maybe in some less often, but more common than this, t is sometimes another variable. But now here we're looking at v as a variable, but it shouldn't matter what the name of our main variable is, as long as the d expression here is consistent with our variable's name. We're good to go. So that now indeed means we are working with the function h, and we're accumulating. So here it says the accumulation here is from -4 to 4, and it gave us that value being 6. The accumulation here going from -1 to 4, okay, going from -1 to 4, it gives us a value 8.7, okay, and the accumulation that goes from -4 to -1, we need to find that out. We need to evaluate that. But so if we're now looking in that way, then the property that I just now mentioned in the other board have a perfect explanation for this. So the way I see it is, as far as the interval itself, then the -4 to 4 is the longest one. -4 to 4 is the longest interval. And then -1 is somewhere between. Somewhere between. And so h of x is some function above that, like this. And so now definitely as applying that property that I reminded anyone on the other board, then the accumulation now is supposed to be breaking up into. So in this quick illustration picture, then now I need to use my other board. And so now in the way how I see the total interval from -4 to 4, the total accumulation, the total integral from -4 to 4 on this function h of x, h of v, can be broken up according to that picture. And that picture came out as the property of integral that we have just studied earlier, previously. And so this can be broken up as the integral from -4 to -1. And h of v dv is the function, and we need to be accumulating that together with the other function going from -1 to 4 for h of v dv. Okay, for h of v dv. So at that point, so now once we nail down this relationship between the two that connects the three definite integrals, then let's look back at the given information. So the given information gave us this piece of integral to be an 8.7 in numerical value. This piece right here is a 6. Okay, and we're supposed to look for the one from -4 to -1. So now that means in the next step I can see that we're looking at this total interval on the left-hand side, this total integral, this total accumulation from the left on the left-hand side of our equation. That's another point I would like to point out here, is that we can see this as an equation. So we don't have to worry about how the given information obtained that value, but this now is a 6 according to the given information. Okay, and then this is the one that we need to find. So that integral is unknown from -4 to -1, and that's the one we need to evaluate. Okay, and then the next one here was among the given ones, so it's plus 8.7. So now, simply seeing this as a variable, as an unknown that we are solving for, what we have here is simply just a simple equation where we subtract both sides by that 8.7, and that's going to give us our final result. So subtracting 8.7 from both sides. Okay. So it turns out minus minus 2.7, okay, minus 2.7 equal negative equals the integral from -4 to -1 for h of v dv. All right, and so that's how we found the answer. And then to make it a little easier, you can write the integral from -4 to -1 of h of v dv equals minus 2.7. But that's how we are done with our problem. Okay, so we utilize directly that property that we've learned earlier. Okay. All right, so now in the third example I would like to give out, let's look at the following. So now again we are given a couple of known definite integrals. So what about, we have an integral, a definite integral from -9 to 8, and our function here is f of x dx equals 8. Okay, so this is a known definite integral. We already had a known value for that, so we don't even have to worry about how this was done, because we don't even know what that function f of x is. Okay, and then we are given another one, another known definite integral. So what about from -9 to 8, and then here we're looking at g of x. Okay, that was 27, and there's a third one right here, -9 to 8. Okay, on an h of x. And this was known to be 23. So these are all, three known definite integrals. Okay, and then at the end of that given information, we are asked to evaluate. Okay, we want to evaluate the following integral. It's an integral from -9 to 8 on the following function. It's a function that comes out from 9 f of x, 9 times f of x, plus 2 times g of x, and we're going to subtract h of x. Okay, so really this is one function, but what I see in this function here, it's got multiple terms, and some term has a coefficient. Okay, and that's the whole idea right there. All right, so there we go. That's our problem right there. Okay, so into my other board now. So now what I can see here is that the integral from -9 to 8 for 9 f of x plus 2 times g of x minus h of x. This integral, what first caught my attention is that this integral that we're attempting to find a value has multiple terms. There's a plus right here, there's a minus right here. So there are three terms in one function, but three separate terms, and some terms here have even a coefficient in front. Okay, and so directly the sum and the difference rule that I have explained previously, right before we get into these examples here, allows us to break this down into an integral between anywhere from minus 9 to 8 for 9 times f of x dx. And then the first term and the second term was connected by the plus. It was a sum between the first term and the second term. So now I'm breaking it down as, so I'm producing my second integral from minus 9 to 8 again. So same integral limits here. Okay, and then we have 2 g of x. All right, and then between the second term and the third term, it was a subtraction. It was a difference between the two terms there. So that means the next integral being brought in, I need to subtract minus 9 to 8. It's an integral accumulating from negative 9 to 8. And then on this function here, it's h of x dx. All right, so I just directly utilized our rule or our property on the sum and difference of a definite integral to break this total integral down into three separate integrals and adding and subtracting accordingly. Okay, and now if we're looking even further, then this first integral is a function f of x, but function f of x here has a coefficient 9 in front. And so we also had a property where we can keep the 9 in front of the integral. So now it means we only need to know the integral from minus 9 to 8 on the simple function f of x. Now I shouldn't even call that simple. We don't even know how simple or how complicated that is. But what I mean is we simply need to focus to our integral, our definite integral from negative 9 to 8 on that individual function. Okay, so I should have said individual function. And then once we know that integral value, final value, we're going to multiply with 9. As I have already said earlier, we can bring the 9, the coefficient here, in front and multiply with the final integral there. Okay, so we can do the same for the middle term. It's a 2 as a coefficient, constant coefficient, multiplied with g of x. So now I'm going to have plus 2 and minus 9 to 8. Okay, it's accumulation from minus 9 to 8, and then g of x dx. Okay, and then the third term here has no coefficient, so let's leave it the way it is, minus the integral from minus 9 to 8, okay, on the function over the function h of x with the dx. Okay, so now we successfully lay it down and then brought all the constant coefficients in front. So now if we observe a little further, so individually, aside from having that 9, and we already knew a value for this integral, the integral from negative 9 to 8 of the function f of x, because it was among our given information. That is 8 here. Okay, and the other one is 27, and this one here is 23. Okay, so now having all of that given information, now I'm ready to just simply substitute values in. So this integral itself is an 8, so we have 9 times 8. Okay, so I'm putting h in parentheses because that's substitute for the entire integral there. Okay, and then plus, now 2 times this other integral in the middle for g of x is 27. Okay, and then the last one here is a 23, so I'm subtracting 23 like that. Okay, all right, so now the answer comes out 103 according to my calculation. All right, so now we have found that answer here, this integral that came out as a sum and the difference with 3 terms there. That came out down to a final answer 103.